Hi, my name is Bas. Last year, I was a drivetrain engineer in the Delft Hyperloop team. In this video, I'd like to show you around in the world of levitation. I'll give you some advantages of levitation compared to using wheels and explain how some of the most used levitation methods work. First, to get some background, let's have a quick look at wheels. As you know, wheels require bearings. These bearings need to be able to handle high rotational speeds and the load forces of carrying the pods. These bearings are also not frictionless, adding onto the rolling friction that the wheels already have. To reduce this rolling friction, wheels should generally be made of a very hard material. For example, steel train wheels are one of the best wheels in terms of low rolling friction. Unlike levitation, wheels are limited in speed because of excessive heating and centrifugal force. The current record is 574 km per hour by the French TGV. However, such speeds required extremely accurate track alignment and modified wheels that cause huge wear and tear. Therefore, these speeds were never used in regular train services. In many other vehicles, like the Bugatti Chiron, wheels turn out to be a limiting factor in terms of top speed. Levitation is an excellent alternative method of moving at high speeds. There are three big advantages compared to conventional wheel-rail infrastructure, important for us to consider. Firstly, due to the vehicle not making physical contact with the infrastructure they run on, there is virtually no friction, which causes wear and tear on the tracks. This reduces the maintenance costs by improving the longevity of the tracks. Secondly, maintaining ride comfort is much easier to do with levitation. This is because an air gap between the vehicle and track is an excellent absorbing interface for small track imperfections, greatly reducing vibrations during travel and decreasing infrastructure construction costs. Lastly, by using levitation, friction caused by wheels is eliminated. This rolling friction is especially large at high speeds. Because of the reduced friction, levitation will allow for a reduction in energy needed to operate, making it an environmentally friendly option. The cost of the infrastructure for a levitation transport system has also been coming down over the past years due to technological improvements. One can now expect to pay a comparable price for high-speed wheel-rail or levitation infrastructure. However, the fact that the levitation transport system cannot operate on already existing wheel-rail infrastructure is a major setback. The construction of a whole new infrastructure for only a levitation transport system is expensive and not that inviting for countries that already have a high-speed wheel-rail infrastructure. This is one of the major reasons that adoption of, for example, maglev trains has been relatively slow in the West. Although compared to maglev, Hyperloop offers a further increased speed thanks to the vacuum environment, which would further increase the profits thanks to reduced cost per time. More about this in our lectures about infrastructure. Now, we will have a look at different methods of levitation. Levitation always requires some force at a distance acting between the vehicle and the rail. Magnetic levitation is a well-established option and is already being commercially used at high speeds in China and Japan. Another option that has also been proposed by Elon Musk for the Hyperloop is the use of air bearings. Let's first have a look at magnetic levitation. Magnetic levitation comes in two flavors. The first being electrodynamic suspension, or EDS. EDS is a passively stable method that does not need active tweaking of the magnetic fields. This method relies on small electrical currents that are induced in a conducting material when a magnetic field is moving relatively to the conductor. These small electrical currents, known as eddy currents, produce a magnetic field that opposes the change in magnetic field caused by the moving magnets. Resulting from this is a magnetic levitation force. This levitation force is dependent on the relative velocity between magnet and conductor, increasing when the relative velocity increases and vice versa. This means that the force would be too weak for pods at low speeds and completely disappear for stationary pods. This means the pods require additionally landing wheels compared to those of an aeroplane. When designing an EDS system, the magnets can be either attached to the track or to the pod. This does not matter for the effect to work. But when being mounted on the track, many more magnets are needed, since they need to be present along the full length of the track. Additionally, the magnets can either be permanent magnets or electromagnets. The latter, of course, require an electrical power supply. The advantage of using electromagnets is that they can be cooled to very low temperatures to become superconducting. Superconductance allows for these electromagnets to create an exceptionally strong levitation force, which could be required with heavy pods that would be required for transporting a large amount of people or of heavy cargo. In addition to repulsive force, a drag force opposing the direction of movement is also present. This means an EDS system will always have some sort of magnetic drag. However, this drag becomes relatively smaller for higher speeds, which is something that cannot be said about wheels. The other flavor of magnetic levitation is the electromagnetic suspension, or EMS. This works in a very different way. This method is active, meaning that the strength of the magnetic fields of the electromagnet is being controlled via a feedback loop. Unlike EDS, here the electromagnet is placed close to a ferromagnetic material and will exert a strong attractive force, like the magnets on your fridge, for example. This force is dependent on the distance to the object, becoming much stronger when the magnet is closer and weaker when it's further away. Via a feedback loop, the magnetic field strength of the magnet will be lowered whenever the magnet comes close, and vice versa. When the feedback loop is tweaked just right, the magnets will be floating. EMS does not need the same landing wheels that EDS needs, because the levitation force is not dependent on the movement speed. But at the same time, it needs an active control system that could be a point of failure. Apart from magnetic systems, it's also possible to levitate via air bearings. Air bearings thrust air to create a thin film between the pod and the track. The extremely low friction they have can be clearly demonstrated by an air hockey table. The air bearings can be mounted on the vehicle or on the track. But this choice has some design implications. Mounted on the vehicle, they thrust air downwards, while being mounted on the track, they thrust air upwards, similar to the air hockey table. Just like with the magnets, having them installed on the track would mean there needs to be a lot of them. There would be a lot of them since they are required along the whole track. Conversely, in Elon Musk's Alpha paper, he featured a Hyperloop design with air bearings mounted on the vehicle. This pod uses a compressor to suck in the high pressure front that the pod encounters during high speed travel. This air is then redirected downwards through the air bearings for levitation. Air bearings always require some sort of airflow control through an air compression system, be it an air compressor or having valves release compressed air stored on board. In summary, we first looked at wheels and saw how they are speed limited and suffer from wear and tear during use. Secondly, we looked at two different magnetic levitation systems, EDS and EMS. EDS requires no active control system to levitate, but has a minimum liftoff speed and requires landing wheels. EMS does not need landing wheels, but needs an electronic feedback system to maintain its levitation. Lastly, we looked at air bearings. Air bearings create a thin air gap underneath the pod that allows for low friction travel. These do require a form of active flow control and a source of high pressure air. Thanks for watching.